Now we introduce an algorithm for finding an Euler circuit. As we have seen before, an Euler circuit is a path containing all the edges of the multigraph only once, where the first and last vertices are the same. Here are some facts about finding an Euler circuit. Any Euler circuit will need to go through all the vertices of the multigraph because all the edges are used. We can start with any vertex because if there is an Euler circuit, that vertex can be the initial and the last vertex. As we proceed along an Euler circuit, each time a vertex is reached along some edge, there must be another edge that was not visited before for us to exit that vertex. This means that all the vertices must have even degree. Here's the Euler circuit algorithm. Consider this given multigraph. Now we're going to begin with a vertex U and construct the path from U back to U by randomly selecting unused edges for as long as possible. Also, every incident edge to U must be included in this path. If we start at this vertex, then there are only two ways we can go. We can go through edge B or edge A. If we choose edge A, then we arrive at this vertex here. We go through edge G. At this moment, we arrived at this vertex. At that vertex, we have several options. We can go through edge D, C, F, H, or J. Now, it's important to note that for this particular graph here, it's very easy to find an Euler circuit without using any algorithm. By simply looking at the graph, we can figure out a path that will be the Euler circuit. Now, we must realize that the algorithm is for any graph, any given graph. We cannot rely on visualizing the graph. One analogy is to pretend that these edges of the graph are tunnels. And as we go through each tunnel, we arrive at a place where we can select several tunnels. If we are in that tunnel, we have no idea where we're going to. But one thing is for sure, the degree of that particular vertex is even. So if we arrive at one vertex through an edge, we should be able to leave that vertex through another edge. And we can pick the edge randomly. Eventually, we will come back to the original vertex that we started. At this vertex, suppose we're going to choose edge D. Edge D then leads us to this vertex. At this vertex, I could go through E, or C, or B. Suppose that for some reason, or randomly, we chose B. Now we are back to the original vertex. At this point, there is nowhere to go. We already used all the incident edges to this vertex. Now comes the next part of the algorithm. This first cycle, this first part of the algorithm gave us a part of the Euler circuit. Here we have the path A, G, D, and B. Notice that I'm not listing the vertices, but it's understood that once you select this edge, you're selecting this vertex first and this vertex next. Once you select this edge, you're selecting this vertex and then this one next. So that first part of the algorithm will give us the path A, G, D, and B. From the cycle that we found, we pick a vertex that still has incident edges that have not been used and proceed from there. Let's say, for example, we continue from this vertex here. From that vertex, we have four choices. We can go through C, F, H, or J, and we don't go through D or G because those two are already selected. Let's say, for example, we go through edge C. Now we have only one option to exit that vertex. It's through edge E. After arriving at this vertex here, there's only one way to exit. It's through edge F. Now we're back to this vertex. We need to continue until all the incident edges are used. So this vertex here still has two incident edges that have not been used, edge J and edge H. Now we continue. Suppose we choose edge H, and edge H, we arrive at this vertex here. and then edge I. And at this vertex, there is only one choice, which is edge J. Now we are back to this vertex that we started in the second phase of the algorithm. There is nowhere to go. That gives us a new piece of the Euler circuit, which is the path CEFHIJ, which is this path right here, CEFHIJ. That second piece has to be joined with the first one at the appropriate position. Notice that the first piece, the first path, is AGDB. The second piece has to be added between the edges G and D. That's where the initial vertex of the second piece is located. Joining the two pieces, now we obtain an Euler circuit for this particular multigraph. Theorem 4.5 describes the condition that was mentioned before. Number one, if a graph G has an Euler circuit, then that means that every vertex in the graph has even degree. Conversely, if we have a graph where every vertex has even degree, then we are sure that that graph has an Euler circuit. So that's a necessary and sufficient condition for a graph to have an Euler circuit. Number two, a graph G has an Euler path if and only if every vertex has even degree except for two distinct vertices. Those two distinct vertices have odd degrees. In that case, those two are the first and the last vertices of the path. Now let's take a look at this example. We are going to use the Euler circuit algorithm in order to find an Euler path. The idea here is to make all the vertices even degree. Now, if this graph has an Euler path, all the vertices have even degrees except for two. And we can see that this one has degree 3, that one has degree 3. All the other vertices have even degree. In order to make those two odd degree vertices even, we introduce a temporary edge connecting one odd degree vertex to the other odd degree vertex. With that temporary edge, now all the vertices have even degree. Because of that, we are now able to find an Euler circuit. Let's apply the algorithm to this new graph. Let's begin with any vertex. This one here, for example. It doesn't need to be that particular vertex. That one was previously an odd degree vertex, and we introduced the temporary edge to make it an even degree vertex. So we begin with any vertex, and from that vertex we choose an edge randomly, and we proceed to the adjacent vertex. Here we arrive at this vertex, and then we randomly choose an edge. We could choose this loop or this edge. Suppose we choose edge D. We arrived at this vertex. Again, we randomly choose another edge, and we do that until we come back to the original vertex. If I had chosen edge F, for example, then we proceed to the next adjacent vertex, and we continue to do that until we arrive to the original vertex. Here we arrive at the initial vertex. Again, we continue because there are two edges that are incident that have not been chosen. So we go from there. We can randomly choose C or B. We choose C here, for example. From there, we arrived at the adjacent vertex. Here is the vertex. We go, for example, through F. Now, the only edge that is available from that vertex is edge E. Because every vertex has even degree, we are able to arrive and exit that vertex. Here we arrive at this vertex, and let's say we come back to the original vertex through edge B. Now we have used all the edges that are incident to that initial vertex. At this point, we obtain a path made of edges A, D, T, C, F, E, B. The second part of the algorithm is to continue using the vertices that have incident edges that have not been used. For example, let's say we choose now this vertex and then randomly choose an edge, but the only edge that is available is the loop. We choose that one and come back to the vertex. Then we are done here because there are no more edges to choose from. We continue the algorithm by choosing another vertex that has edges that are incident that have not been used. Here, for example, we choose this vertex and we choose this loop. Every time we arrive at a vertex and there are no more edges, no more incident edges that we can choose, we create a path and we join that path to the previous path. So here we had the edge G, this vertex, loop G, and then come back to this vertex. We add that cycle to the original path that we found. Here we found another cycle, or this vertex, the loop H, and this vertex again. We add that to the previous path. Finally, we choose another vertex that has incident edges that have not been used. Here we go through I, no more edges that are incident that we have not used. We add that to the previous path. Now there are no more vertices that have incident edges that have not been used. The final part is to actually delete the temporary edge that we introduced at the beginning. Now when we delete that edge, notice that we create a gap, but that's not a problem. We can simply take the first part of that path and we add to the end of the second part. This way we create a path where the first vertex here is the vertex that is incident with edge C, which is this one, and we go from here, edge C, then we arrive at this vertex and then edge I, as you can see here. And we go through all the edges until we arrive at edge G and then edge D, which is this one. Notice that we arrived at the other vertex that was previously odd. So if we eliminate the edge T, we can clearly see the Euler path going from this vertex to the other odd degree vertex. Now we want to consider a path that uses each vertex of a multigraph once and only once. Those are called Hamiltonian cycles and paths. A Hamiltonian path is a path that contains each vertex once and only once. And a Hamiltonian cycle is a cycle that contains each vertex. Notice that here we don't need to call Hamiltonian circuits because circuits, you may have repeated vertices. But here we can use the word cycle because the vertices are not repeated. From the definition, we go through each vertex only once. Unfortunately, there are not easy criteria for Hamiltonian cycles and paths. The only result that we can see here in this course is theorem 4.6. The theorem says that if you have a graph with more than two vertices, and for every pair of non-adjacent vertices, the sum of their degrees is greater than or equal to the number of vertices, then the graph has a Hamiltonian cycle. For example, this graph has 6 vertices, so n is equal to 6. Now let's add the degrees of any pair of non-adjacent vertices. For example, these two vertices here, each one has degree 3, and if we add the degrees, we have 6, which is equal to n. If we pick any other pair of non-adjacent vertices, this one and this one, the sum of the degrees is 6. Or that one and that one, the sum of the degrees is 6. According to the theorem, this graph has a Hamiltonian cycle. It follows from the theorem that if the degree of each vertex is at least n over 2, then the graph must have a Hamiltonian cycle, because if we pick any pair of non-adjacent vertices, then the sum of their degrees would be n over 2 plus n over 2, which is n. And according to the theorem, if that sum is greater than or equal to n, then the graph has a Hamiltonian cycle.